Hello everyone. In this video, we'll discuss the applications of Gauss law to find electric flux density due to some symmetric charge distributions on the closed surface as applicable to Gauss law, which is called closed Gaussian surface. Let us discuss the characteristics of the Gaussian surface as applicable to Gauss law for symmetric charge distribution. We know Gauss law says the closed surface integration of flux density must be equal to the charge enclosed. If we want to find the unknown electric flux density, the charge distribution should be known. And by applying Gauss law, we can find the unknown flux density on the surface by equating the left-hand side and right-hand side. For that, we need to look at the closed surface for which the Gauss law is evaluated, which is also called as the closed Gaussian surface. For symmetrical charge distributions, when we apply Gauss law, we need to find a closed Gaussian surface that satisfies these two conditions as indicated. Condition number 1 says the flux density on the surface, ds, should be everywhere either normal to the surface or tangential to the surface. Let us discuss that with a small diagram. If I consider a closed surface and the flux density vector d is going normal to the surface. If I say d is normal to the surface, the flux density vector should cut the surface and leave out. In this case, the area element ds is normal to the surface, which makes an angle of 0 with the flux density vector on the surface. That gives the dot product between ds and surface element as the maximum value, which indicates this ds is constant also. The second case is d should be either tangential or normal. If I consider d is tangential to the surface, the flux density vector should run parallel to the surface. Here, for the case of the tangential d vector, I have taken the example of circular disk as the surface, and the flux density vector is running parallel to the surface. In this case, the surface element is normal to the surface, and the angle made between the flux density vector and the surface element is 90 degrees. This gives the dot product as 0. There are two cases. If d is normal to the surface, d dot ds is a non-zero value. And if d is tangential to the surface, d dot ds is a 0 value. This talks about the condition number 1 to be satisfied for the closed Gaussian surface chosen. The second condition is if d dot ds is non-zero, that can happen only if d is normal to the surface. For this condition, this d should be constant throughout the surface. When can d be constant? If the closed surface of sphere is at a constant radius, then throughout the surface, the flux density vector d can be taken as constant. So this is an example where if the Gaussian surface is a sphere and everywhere on the surface of the sphere, d is constant. So this ds can be taken as constant in the integrand evaluation for Gauss law, where the integrand is dot product of d and the area element. Taking these two conditions, we will choose the closed Gaussian surface accordingly for any symmetric charge distributions. And we will apply this Gauss law, evaluate the left-hand side, evaluate the right-hand side, equating the two with the known value of charge, we can find the unknown d on the surface of the closed Gaussian surface. Let us discuss about the applications one by one for few symmetric charge distributions, starting with a point charge. If we consider a point charge q, which is a positive charge, the flux density will be radiating radially outward, and we can follow spherical system for our convenience for the point charge evaluation. We know Gauss law says closed surface integration of d over the surface must be equal to the charge enclosed. To satisfy the two conditions, which we discussed just now. The closed Gaussian surface around the point charge must be in the form of a sphere of radius r. When we look at the d vector, which is everywhere normal to the surface, that is, everywhere on the surface, d cuts the surface and leaves out. And everywhere on the surface, d is constant because the radius of the closed Gaussian surface is same. In this case, the radius of the closed Gaussian surface is taken as r, and the variables are theta and phi. To cover the complete sphere, theta should take the values 0 to pi, and phi should take the values 0 to 2 pi. We can now perform the evaluation of charge enclosed and the left-hand side, that is closed surface integration of d dot ds. Equating the two, we can estimate the unknown d. For the closed Gaussian surface in the form of sphere, radius is constant. The variables are theta and phi. With the variables theta and phi, we can write the area element as r square sine theta d phi ar cap. And we know the flux density is radially outward. So the direction is only in ar direction. The integrand of the Gauss law, that is d dot ds, should be evaluated. Taking dot product of d vector on the surface and the area element, we'll get dr r square sine theta d phi as the integrand of left-hand side evaluation. We can perform this integration over the entire surface of the sphere with the theta limits extending between 0 and pi and phi limit extending between 0 and 2 pi. And we know d is constant. We can take outside the integration. Thereby, the integration of sine theta d phi is going to give 4 pi r square times dr. This is the left-hand side evaluation. And we also know the right-hand side is the charge enclosed. In our case, the charge enclosed is the point charge of Q. We can equate the left-hand side and the right-hand side to get the unknown vector d. Equating the two will give dr as q by 4 pi r square, and the vector d is in radial direction, which includes ar cap as the direction vector. We know the relation between electric field intensity and flux density in terms of the permittivity. So electric field intensity can be estimated as d vector over epsilon, that is q by 4 pi epsilon r square ar cap for point charge.